Section. Introduction. We're going to talk about a growing issue in the field of language model development. As the size of the training data for these models increases, developers, such as those behind GPT-4 and Llama 2, are becoming less willing to share the specifics of their data sources. This lack of transparency creates problems for evaluating these models scientifically and ethically. For instance, private information could be unintentionally revealed during the training process. Past studies have shown that language models can generate text from copyrighted books and personal emails, which could infringe on the rights of the original authors and violate their privacy. Moreover, the training data might unintentionally include benchmark evaluation data, making it hard to accurately assess the model's performance. In this paper, we're looking into the problem of detecting pre-training data. Given a piece of text and a language model that we don't know the training data of, can we figure out if the model was trained on that text? We're introducing a benchmark, Wikimia, and a method, MINK%PROB, to tackle this problem. This issue is a type of membership inference attacks, MIAs, a concept first proposed by. Recent studies have looked at detecting fine-tuning data as an MIA problem. However, applying these methods to detect the pre-training data of large language models presents two unique challenges. First, unlike fine-tuning, which usually runs for multiple rounds, pre-training uses a much larger dataset but only exposes each instance once, reducing the potential for memorization that's needed for successful MIAs. Second, previous methods often depend on one or more reference models, trained in the same way as the target model, to achieve precise detection. This isn't possible for large language models, as the training distribution is usually not available and training would be too costly. Our first step to address these challenges is to establish a reliable benchmark. We're introducing Wikimia, a dynamic benchmark designed to periodically and automatically evaluate detection methods on any newly released pre-trained language models. By using the Wikipedia data timestamp and the model release date, we select old Wikipedia event data as our member data, i.e., data seen during pre-training, and recent Wikipedia event data, e.g., after 2023, as our non-member data, unseen. Our datasets have three desirable properties: they're accurate, general, and dynamic. MIA methods for fine-tuning usually adjust the target model probabilities of an example using a shadow reference model that's trained on a similar data distribution. However, these approaches aren't practical for pre-training data detection due to the black box nature of pre-training data and its high computational cost. Therefore, we're proposing a reference-free MIA method, MINK%PROB. Our method is based on a simple hypothesis. An unseen example tends to contain a few outlier words with low probabilities, whereas a seen example is less likely to contain words with such low probabilities. MINK%PROB calculates the average probabilities of outlier tokens. MINK%PROB can be applied without any knowledge about the pre-training corpus or any additional training, departing from existing MIA methods, which rely on shadow reference models. Our experiments show that MINK%PROB performs better than the existing strongest baseline by 7.4% in a UC score on WIKIMIA. Further analysis suggests that the detection performance correlates positively with the model size and detecting text length. To verify the applicability of our proposed method in real-world settings, we perform 3 case studies: copyrighted book detection, privacy auditing of language models, and dataset contamination detection. We find that MINK%PROB significantly outperforms baseline methods in both scenarios. From our experiments on copyrighted book detection, we see strong evidence that GPT-3 is pre-trained on copyrighted books from the Books 3 dataset. From our experiments on privacy auditing of machine unlearning, we use MINK%PROB to audit an unlearned language model that is trained to forget copyrighted books using machine unlearning techniques and find such model could still output related copyrighted content. Furthermore, our controlled study on dataset contamination detection sheds light on the impact of pre-training design choices on detection difficulty. We find detection becomes harder when training data sizes increase, and occurrence frequency of the detecting example and learning rates decrease. Section Summary. In this section, the authors discuss the lack of transparency in disclosing the composition and sources of data used to train large language models, LLMs, which poses challenges for scientific evaluation and ethical deployment. They propose a benchmark called Wikimia and an approach called MINK%PROB for detecting the pre-training data of LLMs. MINK%PROB is a reference-free method that computes the average probabilities of outlier tokens, and it outperforms existing methods in detecting the pre-training data. The authors also demonstrate the applicability of their method in detecting copyrighted books, privacy auditing of LLMs, and dataset contamination detection. Section: Pretraining data detection problem. We're looking into the issue of pretraining data detection, which is about figuring out if a certain piece of text was part of the training data. This problem presents unique challenges that weren't present in previous studies on fine-tuning data detection. To help us evaluate methods of pretraining data detection, we've put together Wikimia, the first benchmark of its kind. Let's define the problem and its challenges. We're using the standard definition of the membership inference attack, MIA. Here's how it works. We have a language model, let's call it f_theta, and its associated pretraining data, which we'll call D. This data is made up of samples, z_I, from an underlying distribution, also called D. Our goal is to create a detector, H, that can figure out if a random data point, X, is part of the training data. We're assuming that the detector can only access the language model as a black box, but it can calculate token probabilities for any data point, X. The first challenge is that we don't always have access to the pretraining data distribution. Previous state-of-the-art MIA methods for data detection during fine-tuning typically use reference models to calculate the background difficulty of the data point and to calibrate the output probability of the target language model. These reference models usually have the same architecture as f_theta and are trained on shadow data, which is sampled from the same underlying distribution, D. These methods assume that the detector can access the distribution of the target model's training data and a sufficient number of samples from D to train a calibration model. However, this assumption isn't always realistic because such information isn't always available. Even if we could access it, pretraining a reference model on it would be extremely computationally expensive given the large scale of pretraining data. So, in summary, the pretraining data detection problem aligns with the MIA definition but includes an assumption that the detector has no access to pretraining data distribution, D. The second challenge is the difficulty of detection. Pretraining and fine-tuning differ significantly in the amount of data and compute used, as well as in optimization setups like training epochs and learning rate schedules. These factors significantly impact detection difficulty. It's intuitive to think that detection becomes harder when dataset sizes increase and the training epochs and learning rates decrease. We have some theoretical evidence that supports these intuitions. For example, if we have an example, Z, from D, and the model output is f_theta, Z, and we have another example, Y, that's not part of the pretraining data, it becomes challenging to determine whether an example, X, was part of the training set if the outputs, f_theta, Z, and f_theta, Y, are similar. The degree of similarity between f_theta, Z, and f_theta, Y, can be quantified using the total variation distance. According to previous research, the bound on this total variation distance is directly proportional to the occurrence frequency of the example X, learning rates, and the inverse of dataset size, which implies the detection difficulty correlates with these factors as well. We've created a dynamic evaluation benchmark called Wikimia. We built this benchmark using events added to Wikipedia after specific dates, treating them as non-member data since they are guaranteed not to be present in the pretraining data. We collected recent event pages from Wikipedia, setting January 1, 2023, as the cutoff date and considering events occurring after 2023 as recent events, non-member data. We used the Wikipedia API to automatically retrieve articles and applied two filtering criteria. The articles must belong to the event category, and the page must be created after 2023. For member data, we collected articles created before 2017 because many pre-trained models were released after 2017 and incorporate Wikipedia dumps into their pre-training data. We also filtered out Wikipedia pages lacking meaningful text. Given the limited number of events post-2023, we ultimately collected 394 recent events as our non-member data, and we randomly selected 394 events from pre-2016 Wikipedia pages as our member data. The data construction pipeline is automated, allowing for the curation of new non-member data for future cutoff dates. Section Summary. The section discusses the problem of pre-training data detection, which involves detecting whether a piece of text is part of the training data. The challenges in this problem include the unavailability of the pre-training data distribution and the difficulty in detecting the membership of a data point due to differences in data size, training epochs, and learning rates between pre-training and fine-tuning. To address these challenges, the authors propose Wikimia, a benchmark for evaluating methods of pre-training data detection, which is constructed using recent events added to Wikipedia as non-member data. Section: Benchmark setting. We're going to discuss a benchmark setting that's used in practice. Often, users of language models, LMs, need to identify texts that have been paraphrased or edited. Previous research using membership inference attacks, MIA, has only focused on detecting examples that are identical to the data used during pre-training. It's still unclear whether MIA methods can be used to identify paraphrased examples that have the same meaning as the original. So, in addition to the original setting, we're introducing a paraphrase setting. We use ChatGPT to paraphrase the examples and then check if the MIA metric can effectively identify examples that are semantically equivalent. Also, previous MIA evaluations usually combine data of different lengths in evaluation and report a single performance metric. However, our findings show that the length of the data significantly affects the difficulty of detection. Shorter sentences, for instance, are harder to detect. Therefore, different data length categories may result in different rankings of MIA methods. To explore this further, we propose a different length setting. We cut the Wikipedia event data into different lengths, 32, 64, 128, 256, and separately report the performance of the MIA methods for each length segment. Next, we introduce a pre-training data detection method called min-k%prob that uses the minimum token probabilities of a text for detection. This method is based on the idea that a non-member example is more likely to contain a few outlier words with high negative log likelihood, or low probability, while a member example is less likely to contain words with high negative log likelihood. Consider a sequence of tokens in a sentence, denoted as x equals x1, x2, xn. The log likelihood of a token, she, given its preceding tokens, is calculated as the log of the probability of she given x1, xi1. We then select the k% of tokens from X with the minimum token probability to form a set, min k%, X, and compute the average log likelihood of the tokens in this set. We can detect if a piece of text was included in pre-training data simply by thresholding this min k%prob result. We evaluate the performance of min k%prob and baseline detection methods against LMs such as Llama, GPT-Neo, and Pythia on Wikimia. Our experiments use Wikimia of different lengths, 32, 64, 128, 256, original and paraphrase settings. We evaluate the effectiveness of a detection method using the true positive rate, TPR, and its false positive rate, FPR. We plot the ROC curve to measure the trade-off between the TPR and FPR and report the AUC score, the area under ROC curve, and TPR at low FPRs, TPR at 5% FPR, as our metrics. We use existing reference-based and reference-free MIA methods as our baseline methods and evaluate their performance on Wikimia. These methods only consider sentence-level probability. Specifically, we use the loss attack method, which predicts the membership of an example based on the loss of the target model when fed the example as input. In the context of LMs, this loss corresponds to the perplexity of the example. Another method we consider is the neighborhood attack, which uses probability curvature to detect membership. This approach is identical to the Detect-GPT method recently proposed for classifying machine-generated versus human-written text. Finally, we compare with membership inference methods proposed in previous studies, including comparing the example perplexity to zlib compression entropy, to the lower-cased example perplexity, and to example perplexity under a smaller model pre-trained on the same data. For the smaller reference model setting, we use different smaller models for different larger models. The key hyperparameter of min k%prob is the percentage of tokens with the highest negative log likelihood we select to form the top k% set. We performed a small sweep over 10, 20, 30, 40, 50 on a held-out validation set using the Llama 60B model and found that k equals 20 works best. We use this value for all experiments without further tuning. As we report the AUC score as our metric, we don't need to determine the threshold value. Section Summary. In this section, the authors discuss the benchmark setting for their membership inference attack, MIA, method. They introduce a paraphrase setting to assess if the MIA metric can effectively identify paraphrased examples that convey the same meaning as the original. They also propose a different length setting to investigate the impact of data length on detection difficulty. Additionally, they introduce their pre-training data detection method called min-k%prob, which leverages minimum token probabilities of a text for detection. They evaluate the performance of min-K% PROB and baseline detection methods against various language models using different datasets and metrics. The implementation details and results are also provided. Section: Main Results. We've conducted a series of experiments to compare our method, which we call min-K% PROB, with other baseline methods. The results show that our method consistently performs better across a variety of language models, both in their original form and when paraphrased. On average, min-K% PROB achieves an AUC score of 0.72, which is a 7.4% improvement over the best-performing baseline method. This shows that our method is effective and versatile in detecting pre-training data from various language models. We've also looked into factors that might affect the difficulty of detection. We focused on two aspects: the size of the target model and the length of the text. We found that larger models tend to have more parameters and are therefore more likely to memorize the pre-training data. This means that as the model size increases, so does the AUC score of the methods. Similarly, longer texts contain more information that the target model can memorize, making them easier to distinguish from unseen texts. As a result, the AUC score of different methods increases as text length increases. We've also applied min-K% PROB to real-world scenarios to detect copyrighted books and contaminated downstream tasks within language models. We've shown that our method can detect potential copyright infringement in training data. For example, we used min-K% PROB to detect excerpts from copyrighted books in a dataset that may have been included in the training data of a popular language model. To validate our method, we created a set of 10,000 examples using 50 books known to be memorized by the language model and 50 new books that could not have been in the training data. We then determined the optimal classification threshold by maximizing detection accuracy on this set. We applied this threshold to a test set of 10,000 excerpts from 100 books known to contain copyrighted content. Our method achieved an AUC of 0.88, outperforming baselines in detecting copyrighted books. We found that nearly 90% of the books have a contamination rate over 50%. We also used min-K% PROB to detect information leakage in downstream task data. This is a challenging issue due to the lack of access to pre-training datasets. We created a contaminated pre-training dataset by inserting examples from downstream tasks into a pre-training corpus. We then evaluated the effectiveness of our method at detecting leaked benchmark examples. Our results show that min-K% PROB is effective in detecting information leakage in downstream task data. Section Summary. The authors compare the performance of min-K% PROB with baseline methods and find that min-K% PROB consistently outperforms all baseline methods in detecting pre-training data from various language models. They also investigate the factors influencing detection difficulty, such as the size of the target model and the length of the text. Additionally, min-K% PROB is applied to real-world scenarios, including detecting copyrighted books in pre-training data and identifying information leakage from downstream tasks into pre-training corpora. Section: Main Results. Let's delve into the main findings of our study. We discovered that the method we call min-K% PROB outperforms all other methods we tested. When we looked at the true positive rate at a 5% false positive rate, we found that min-K% PROB showed a 12.2% improvement over the best-performing method we compared it to. We also conducted simulations using datasets that had been intentionally contaminated. This allowed us to study the effects of various factors on the difficulty of detecting the contamination. We found that the difficulty of detection increased as the frequency of data occurrence and learning rate decreased. The impact of the size of the dataset on detection difficulty depended on whether the contaminants were outliers in the distribution of the pre-training data. We created contaminated datasets of various sizes by mixing fixed downstream examples with different amounts of red pajama data. Despite our theory suggesting that larger datasets would make detection more difficult, we found that the area under the curve, AUC, scores actually increased with the size of the pre-training dataset. This suggests that language models are better at memorizing outliers. We hypothesize that this enhanced memorization makes it easier to detect contaminants using perplexity-based metrics. To test our hypothesis, we created control data where the contaminants were not outliers. We used real-time data from August 2023, which was not included in the Llama pre-training. We created 3 synthetic corpora of different sizes and found that AUC scores decreased as the dataset size increased. This suggests that while it becomes easier to detect outlier contaminants as the size of the data increases, it becomes harder to detect in distribution samples from the pre-training data distribution. We also studied the relationship between detection difficulty and data occurrence. We created a contaminated pre-training corpus by inserting multiple copies of each downstream data point into a pre-training corpus. We found that AUC scores positively correlated with the frequency of the examples. We also looked at the effect of varying learning rates on the detection statistics of the contaminant examples. We found that increasing the learning rate from 0.00001 to 0.0001 significantly increased AUC scores in all the downstream tasks. This suggests that higher learning rates cause models to memorize their pre-training data more strongly. We also explored how our proposed technique can be used for auditing machine unlearning, which is important for ensuring compliance with privacy regulations. The right to be forgotten is a legal obligation that allows users to request the removal of their data from trained models. Machine unlearning has emerged as a solution for this, and various methods have been introduced. We tested a novel approach for performing machine unlearning on language models, which involves further fine-tuning the models with alternative labels for specific tokens. We found that this method was effective at unlearning information from the Harry Potter book series. In our experiments, we used two settings to extract the contents related to Harry Potter from the unlearned model: story completion and question answering. In story completion, we identified suspicious chunks from the original Harry Potter books using min-k%prob. We then used the unlearned model to generate completions and compared them with the expected continuation. In question answering, we generated a series of questions related to Harry Potter. We filtered these questions using min-k%prob, and then used the unlearned model to produce answers. These answers were then compared with the expected answers generated by a language model and subsequently verified by humans. Section summary. The main results of the paper show that the min-k%prob method outperforms all other baselines in detecting contaminated datasets. The empirical analysis confirms that detection becomes more challenging as data occurrence and learning rate decrease, and the effect of dataset size on detection difficulty depends on whether the contaminants are outliers relative to the pre-training data distribution. Additionally, the paper demonstrates the effectiveness of the proposed technique in auditing machine unlearning to ensure compliance with privacy regulations. Section. Identifying suspicious texts using min-k%prob. We're going to explain how we identify suspicious text segments using a metric we call min-k%prob. To start, we take the first 4 Harry Potter books and break them down into sections of 512 words each, giving us around 1,000 sections. We then calculate the min-k%prob scores for these sections using two models: the Llama 2-7b Who is Harry Potter model and the original Llama 2-7b chat model. We're looking for sections where the process of unlearning might not have worked properly. To do this, we compare the min-k%prob scores from the two models. If the ratio of the scores falls between 1 divided by 1.15 and 1.15, we label that section as a suspicious one where unlearning might have failed. We found 188 such sections. Interestingly, if we only used perplexity as our metric, we wouldn't have found any suspicious sections. Next, we test the Llama 2-7b Who is Harry Potter model with these suspicious sections to see how well it can continue the story. For each suspicious section, we give the model the first 200 words and then generate 20 possible continuations for each section. The results were surprising. We found that the model could still generate continuations that were very similar to the original story. For example, 5.3% of the generated continuations had a similarity score of 4 or higher when compared to the original continuation. We compared these completed stories to the original storylines using two different metrics: the SIM-CSE score and the GPT-4 score. We found a significant number of sections where the model's continuations closely matched the original story. For example, 10 sections had a similarity score of 4 or higher according to the GPT-4 evaluator. We also found that all of these sections had SIM-CSE scores above 0.7. We should note that we only used the first 4 Harry Potter books for this study. If we included all 7 books, we might find even more sections where unlearning failed. Next, we generated 1,000 Harry Potter-related questions by asking GPT-4 for a list of questions and answers related to Harry Potter. We then used the same process as before to identify questions where unlearning might have failed. We found 103 such questions. We then used the unlearned model to generate answers to these questions. We compared these answers to the ones provided by GPT-4 using a measure called Rouge-L recall, which calculates the ratio of overlapping words between the candidate and reference answers to the total number of words in the reference answer. A higher Rouge-L recall value means a greater overlap, which could indicate a failure of unlearning. Among the 103 selected questions, we found an average Rouge-L recall of 0.23. For the unselected questions, the average Rouge-L recall was 0.10. These results show that our min-K% PROB metric can effectively identify instances where unlearning might not have been successful. Finally, we want to talk about membership inference attacks, MEAs, in natural language processing. MEAs aim to figure out if a specific sample was part of a model's training data. These attacks can pose serious privacy risks and can be used for more severe attacks, like data reconstruction. Because of these risks, MEAs have been used to measure privacy vulnerabilities in machine learning models and to check if privacy-preserving mechanisms have been implemented correctly. While MEAs have been used with tabular and computer vision data, they've only recently been applied to language tasks. However, most of this work has focused on fine-tuning data detection. Our work is unique in that it applies MEAs to pre-training data detection, an area that hasn't received much attention in previous research. Section Summary. The section describes the process of identifying suspicious texts using the min-K% PROB metric. By comparing the scores between two models, suspicious chunks that may have failed the unlearning process are identified. The study also applies the min-K% PROB metric to select Harry Potter-related questions and assesses the accuracy of the unlearned model's answers. Additionally, the section introduces the concept of membership inference attacks, MEAs, and highlights the application of MEA to pre-training data detection, an area that has received limited attention in previous research efforts. Section. Dataset contamination. The issue of dataset contamination in language models, LMs, has recently come under the spotlight. This is because the integrity of benchmark evaluations is compromised if the examples used for evaluation are inadvertently exposed during the pre-training phase. Several studies have addressed this issue. Some researchers define an example as contaminated if there's a 13-word overlap between the training data and the evaluation example. Others have refined this approach by considering an example as contaminated if 70% of its 8-word sequences are found in the training data. Further advancements in this field have seen the development of methods that extend this framework to tokenized inputs. In this case, a token is judged as contaminated if it appears in any token sequence longer than 10 tokens. However, these methods have a limitation. They require access to retraining datasets, which are often not available for recently released models. In response to this, alternative approaches have been developed that aim to detect contamination without needing access to pre-training datasets. One such method involves prompting ChatGPT to generate examples from a dataset by simply providing the name and split of the dataset. It was discovered that the models generate exact copies of instances from natural language processing datasets. This framework was further expanded to extract more memorized instances by incorporating partial instance content into the prompt. While these methods have been useful in studying contamination in closed-source models, they fall short in determining contamination at the level of individual instances.